Okay, so we're going to work a couple of problems over what's known as the common ion effect. Well, one problem with regards to the common ion effect, and then we'll work another problem which will ask the question, if you mix two solutions together, will precipitation occur? Okay, so if we had CaC2O4 and water, which ionizes again to give calcium 2 plus and C2O4 2 minus. So if we had a beaker of that setup, so there's some CaC2O4 that does not dissolve, so it's solid, and a little bit of calcium, and a little bit dissolves though, so you get some calcium in solution and some C2O4 2 minus in solution. And then if we have a second solution of calcium chloride in water. And so what's significant about this is calcium chloride is very soluble in water. So if you add it to water, then it totally dissolves to give calcium 2 plus and 2 chloride minus ions. So let's say we have a 0.15, so if we made a 0.15 molar solution, so at the start there's no calcium, no chloride, and then at equilibrium, since this is much more soluble than the CaC2O4, then the calcium chloride is essentially gone, and it's all dissolved, so there's all calcium and chloride and no solid left behind. Okay, so now what we want to do is we want to take those two solutions and mix them together. And so the question is basically what happens, so how does calcium chloride affect the solubility of CaC2O4? And so what's significant, or what you have to recognize here, is that since this is totally dissolved, you're basically adding some calcium ions to this equilibrium. And so what's going to happen to, let's call this equilibrium A and equilibrium B. So what's the calcium 2 plus ions? So what will the calcium 2 plus ions from CaCO2 do to solubility of CaC2O4? So if you remember from the last chapter, Le Chartier's principle, so when you mix the two solutions, you basically now have some calcium 2 plus ions already present in solution, and so by Le Chartier's principle that should make this equilibrium A go backwards, and so CaC2O4 should become less soluble. So we'll do the math to illustrate that. So we'll try this equilibrium again. And so now the start, for calcium 2 plus is 0.15 molar, because that came from the calcium chloride. And the C2O4, so the start of the dissolving of the CaC2O4, there's no C2O4 2 minus in solution, but there already is some calcium 2 plus in solution because of the calcium chloride that was present. And so then at equilibrium, there's now 0.15 plus X of this, and there's X of that. Okay. So we want to solve for, so KSP is 2.3 times 10 to the minus 9. So 2.3 times 10 to the minus 9 is equal to 0.15 plus x times x. And then we can simplify this equation because k is so small. This x is going to be extremely tiny. So 0.15 plus x is essentially the same as 0.15. So then x is equal to 2.3 times 10 to the minus 9 divided by 0.15, which is 1.5 times 10 to the minus 8. So the molar solubility of CaC2O4 in 0.15 molar calcium chloride is 1.5 times 10 to the minus 8 molar. So in pure water, however, so the molar solubility of CaC2O4 in pure water is 4.8 times 10 to the minus 5. So you could get that number basically if you went back to this, and if the 0.15 was not there and you just had x times x and solve for x, then you would get that x is 4.8 times 10 to the minus 5. So if we just take these two numbers and divide them, so this is how much dissolves in pure water, divided by the 1.5 times 10 to the minus 8. This is how much dissolves in the 0.15 molar CaCO2. So if you calculate that out, you get 3,200. So that basically means that CaC2O4 is 3,200 times more soluble in pure water than it is in 0.15 molar calcium chloride. And that's because the calcium that's present by Le Chartier's principle shifts the equilibrium back to the left and suppresses the CaC2O4 from dissolving. And so that's what's known as the common ion effect. If you add a common ion, that's going to shift the equilibrium in the opposite direction.